Okay, ready? So this is a chapter on the force and pressure. All right. So some of this you learn in Sec 2, but don't worry, I'll still go through again. Now down here, I think the key thing you must understand about forces is there are two kinds of forces. One is the contact force, one is a non-contact force. A contact force means there's direct contact between two bodies, objects. Okay. And a non-contact force means they can influence each other, attract or repel, but they do not have any physical contact. So the contact forces are like friction. The two surfaces must touch each other. Air resistance is a form of friction also, because when you move through the air, the friction between the object surface and the air is called air resistance. Tension is when you have a force and pull. Okay. Normal force is when you push on the let's say a wall. The perpendicular force that acts towards you or acts back towards you is called normal force. Or you put the object on some surface, the force that's acting outward is called a normal force. So all these are contact forces. So for them, memorize friction, air resistance, tension, and normal force. For the non-contact force, this one you must memorize also. Gravitational force, electrostatic force. Gravitational force is the gravity acting on us by Earth. And that's what we know. But actually, every object has some gravitational force acting on each other. For example, you have certain gravitational force acting on objects around you. But because our mass is so small, the force is very negligible. But if the object is very big, like the Earth mass or maybe planet or sun, the gravitational force can be very, very large. All right. Electrostatic force has to do with charges. Charges like positive, negative charge. Okay, and then magnetic force is a north and south attraction, and of course north and south can attract matter and so on, so those are called magnetic forces. Okay, so these are the three example of the non-contact forces. So force is a physics concept used to explain why stationary objects start to move and why moving objects can change their motion. When you change the motion, it could mean change direction, can slow down, all right, can speed up and so on. All right, so let's move on. So these are the different kind of forces. For example, when you kick a ball, okay, it causes a stationary ball to move. So it's kicking a ball to start moving. Or you stop a ball from going into the net. So you actually stop a moving ball, stop moving. Or it can cause the moving ball to move faster. Or moving ball to move slower. Or you can say a moving ball change direction. So all these are the examples of what the force can cause. Stationary can start to move. If it's moving, it can stop. While it's moving, it can even go faster, slower, or even change direction. So these are all the effects of the forces on motion. Okay, effect on motion. But of course, forces can have other effects also. Later we look more. So force is a concept that cannot be seen directly. However, we know the force exists by observing the effects on motions. All right, so that's why we see, for example, if you're sitting in a room, you're reading, let's say in a room now, you're reading, you're doing a revision. Suddenly you see your cup move. Will you be scared?
Yeah.
Why?
Because it's like out of nowhere.
Yeah, correct. You don't see a force. There's no force around. How come it can move, right? So if somebody push it or the wind blow and then the ball start rolling, you say, okay, I know, because you can understand there's something invisible, but it's logical. You can deduce. But in a room there's totally nothing moving, no wind, and then the cup start moving, you'll be so scared. There must be some kind of forces. So when the forces cannot explain, people call it what, spiritual or metaphysics and kind of thing. Yeah, possible, right? So anyway, down here, just imagine a force causes a motion. All right. So down here, the force can be, these are the detailed explanation. For example, a tension is basically pulling force. To and pull is called tension. Normal force is when you act on something, then the reaction force acting back is called the normal force. You see? A force that arises due to contact between two objects. So usually it's perpendicular to the surface of contact. So likewise, when you have a wall and your hand push against the wall, so the normal force is what? The normal force will be this. See that? It's always perpendicular to the force that you're acting on a surface. So if you're standing, the normal force is here on the leg, vertically up. Okay, so it's always perpendicular to the surface of contact. These are the key points. So it's due to the contact between object and it's perpendicular to the surface of contact. Okay, so I place a cup on the table. The table force acting up is called the normal force. Okay. Now friction, when you push, friction is the force that opposes motion. I think it's very important to learn this keyword, opposes motion. Oppose motion. So friction will slow down, okay, an object. If it's moving freely, it will slow it down because it opposes the motion. And usually when you say smooth surface in the exam, you say smooth surface, you can assume there's no friction. If you never mention rough, but never mention smooth, you can assume that there is some friction. Of course, when you mention rough, means there's a lot of friction. Okay, so smooth surface generally talk about frictionless. Okay, air resistance, like I say, is actually again opposed to motion. It's a form of friction. What kind of friction? Friction between the object and the air molecules, the friction. So air resistance can produce heat also. You know, like for example, the rockets, okay, or space shuttle coming back from the outer atmosphere back to Earth, you know, it can become very, very hot. It can actually burn. All right. So because of air resistance, the air rubbing against the surface. So down here, these are the four forces you must know. Tension, normal, friction, air resistance, they're all contact forces. Contact forces. Now, next one. Gravitational force is due to the force that pulls any object towards the Earth or any body. As long as you got mass, there's gravitational force. Electrostatic force is between charged object. So generally, you're talking about a positive and a negative attraction. Okay, positive negative attraction. Magnetic force is between, of course, north and south, or at least they can induce the metal to become, for example, if this is north, for example, this is north, this is south, I can induce this to be north, to be south, and then attract. So we put a magnet near to an object. You actually, if the object is not a magnet, you actually make it magnetized. For example, I have a magnet like that, north, south, and this is iron. So the iron will be induced to form a north and a south. So this will cause this end to become magnetized. That's why it attract. So no matter what, attraction is always between north and south. So this one cause it to magnetize, then it attract because opposite poles will attract. Can I say that? Yeah. All right. So let's look at common error. Non-contact forces only occur when objects are not touching each other. Is it true? Is it non-contact force occurs only object not touching when they're not touching? What happens when they touch? For example, a magnet. Okay, magnet is a non-contact force. Without contact, they already have a force. But if the magnet are attracted and touch each other, can I say that the magnetic force turn into a contact force? No, it's still non-contact force. That means, in other words, non-contact force means you don't need contact to have interaction. Don't need the contact, but they can be touching. Okay, so non-contact force will also occur when they are touching each other, but you don't need them to touch. Are you with me?
Yeah.
Can I say? So you must differentiate. In case MCU come out, non-contact means they cannot be touching, no that. So a non-contact force like magnetic force is still a non-contact force, despite the fact that they attract and touch. See, attracting is still a non-contact force because you don't need to be contact, but it does contact. Okay. All right, here. What's this? Let me see. Oh, this is a special kind of train called the funicular. Is pulled by steel ropes and bring people up the hill. So basically, is I can't remember see what exactly what is it. It's pulling up the hill. All right. So a simple model represent the funicular is a block A on a smooth inclined surface. When you mention the word smooth, there we can say that no friction. Okay, whenever you see the word smooth, you can assume that there's no friction. All right, with a string tie over here, name the forces that act on A. Now think carefully, what kind of force act on A? Maybe just name some.
Gravitational.
Yes, of course, the gravitational, right? So the gravitational force is vertically down, not like that, not this one. This is not. Okay, it's vertically down, but because there's a slope, even though you are vertically down, you still will slide down the slope because of the gravitational force. Now, again, when the body is in contact each other, there's a force that's perpendicular to the contact, right? What do you call that? Right, N. Can you remember?
No. Wait. Huh? Wait. Can you repeat that?
A force between two objects in contact. So this object is on the surface. So this perpendicular force is called?
Normal reaction.
Yeah, the normal force, all right? Let me see what they have here. Let me see. Okay, normal force. Okay. So because it's in contact with the surface, it experiences a normal force acting perpendicular up. So this is normal. Normal force. And this is gravitational force. Kg. And there's one more. There's one more tension here. Okay, tension. Let me see, where is it? Tension. Tension itself is a force. Okay, there are three of them. Can I say?
Yeah.
Right. And the surface is smooth. Take note of this point. I mentioned again, when it's smooth, means no friction. Remember that. If it's not smooth, then there's a friction. Because if you're moving up, then the friction is actually here between the surface. Is it okay? Yeah. But in this case, smooth, no friction. So I delete away, no friction. That's all. So your three forces: gravitational force, tension, and normal force. Right. So what does normal in terms of normal force refer to? Why do you call a normal force?
See?
See? Okay, because perpendicular, yes, correct. Remember our reflection, right? When the ray hits the surface, then you draw this dotted line, then like that, right? This is called normal because it's perpendicular. So normal always means perpendicular. Okay? Right. Now they come to the mass and weight. Now, I believe you remember we have done this before in Sec 2, right?
Mm-hmm.
So the key thing down here in this chapter you need to learn is define what is gravitational field strength. And then you also must remember how to use a formula. The weight is mass times gravitational field strength. Okay, gravitational field strength, in short, we call it gravity, right? We call it the word gravity. Okay, but it's called gravitational field strength. That means how many Newton per 1 kg. Okay, learn that in a short while. And you need to differentiate between the mass and the weight. Like, which one is affected? Which one can change when you move from region to region? All right, and so on. You need to know. So let's look at this. The weight is an example of gravitational force. I did not say gravitational field strength. The word gravitational force is actually the weight because they are both written as Newton, Newton. But the word gravitational field strength refers to 10 Newton per every kg, the strength. You see the difference?
Yeah.
So when you say gravitational force, it's the force. And the force is actually the weight acting downward. So here you need to learn two things. Let me highlight this. First, the mass is the amount of matter in the object. This definition, yeah, I think I also taught my Sec 1 student, Sec 1, yeah, mass. SI unit kilogram, please remember this. The weight is the gravitational force exerted on the object by the Earth. Unit is Newton. Okay, take note of this. And the weight is equal to the mass times gravitational field strength, the G gravitational field strength. Okay? How can All right, so like for example, day-to-day conversation speaking, we say my weight is 41 kg. But the weight is supposed to be what? Newton. It's not supposed to be kg. Kg is mass. So to be correct in terms of physics-wise, if I measure myself 41.5 kg, means is my mass is the 41.5 kg. The weight is not kg, the weight is Newton. So if the Earth gravitational field strength is 10, then the weight, my weight will become weight equal to 41.5 kg multiplied by 10 Newton per kg. This is gravitational field strength. And end up 410 Newton. And this is the weight. Are you with me?
Yeah.
Can? Okay, good. So weight is responsible for all objects falling towards Earth. Now, why do I say weight responsible? Because weight is actually the gravitational force. The force of gravity acting on any object is called weight. So generally, gravitational force is a force that arises between two objects due to their mass. And we always talk about Earth gravitational force because Earth gravitational force is huge enough for us to feel it. But do you know that I have two objects side by side? They have gravitational force between them. They attract each other, but it's negligible. You cannot feel it. All right. So down here, the strength depends on the mass. Okay, how great is the mass? It's an attractive force. It's never a repulsive force. So two things to know. The strength, okay, depends on the mass. It is only attractive force because you can never repel. Two objects will not repel because of gravitational force. And the direction is a vector. Vector means there's a direction. For example, gravitational force that pulls M1 to M2. So this is a force, M1 to M2. M1 pull to M2. This side is gravitational force that pulls M2 to M1. Are you there? Yeah. Okay, so gravitational force of Earth is responsible for keeping the moon in orbit around Earth. So can you imagine how great is our gravitational force to hold the moon in the orbit? And likewise, the sun is holding us in orbit. Yeah. Okay. Instead of using the interaction between two mass to understand gravitational force, we can use the concept of gravitational field. This is what is tested in the recall. So what's gravitational field? It is defined as a region in which a mass experiences gravitational force. Okay, this one I must remember one. Let me just highlight keyword. It's a region, a space, where a mass, as long as you got a mass, you experience a gravitational force, and that's called gravitational field strength. So the bigger the object I have, Earth is a huge object. So the gravitational field strength is very great. The gravitational field is very huge, and the strength is very great. Any question? No. Okay, gravitational field strength is defined as the gravitational force per mass, per kg mass. So you see that? Gravitational field strength is G. G is defined as the force per 1 kg of mass. Let's see how many force per kg. So gravitational field strength is the gravitational force per unit mass. And this new SI unit is Newton per kg. The greater the Newton per kg, the greater is your weight. Okay. For example, Earth. Earth gravitational strength is about 10. But the moon is only 1/6 of the Earth. Let me try. 10 divided by 6 is what? Oh, it's 1.66. So for example, this one, Earth is 10 Newton per every kg. So I will experience 10 Newton of force, the weight, for every kg of my object. But for moon, is 1.67 Newton per kg. So in other words, for 1 kg object, it feels at 10 Newton on Earth because of the gravitational field strength 10 per every kg. But if it's moon on the moon, my every kg only weighs 1.67 Newton, which is slightly heavier. Okay, so in other words, look carefully here. This Earth is 6 times the gravitational field strength of the moon. That's all. Can I say that? Okay, so factors influencing gravitational field strength. The larger the mass, first one is mass. Larger mass, greater gravitational field strength. Second, nearer to the mass. For example, if we are in an orbit that is very far from the sun, for example, the Earth like that, right? This is sun, and this is Earth. And let's say that's Jupiter. Who experience a greater attractive force? Obviously, my Earth, because the nearer to the mass, the greater is the gravitational field strength. Okay, wait, this one is a mistake, not magnetic. Here's gravitational. Okay, this is gravitational field, okay? Let me just copy and paste the word here.
In space, right, there's like absolutely no gravity, right?
No, it has. It has. For example, the Earth is exerting. Let me put the thing down first. Give me a second. Where's my thing? Paste. Oh, so big. I put it over here. Okay, gravitational field. All right, stronger gravitational field. Yeah, sorry, you say in the space there's no gravity. Not true. Not true. What do I mean not true? Okay, let me show you an example. Okay, just imagine this. This is the sun, right? See my this sun. And the earth is going round and round and round in orbit, right? Am I right? So what happened is this. Just imagine if a person falls out of earth, this is earth. A person falls out of earth here. It may not be attracted to the earth, but it's still attracted by the sun. What do I mean? You see, the earth is attracted by the sun and go round and round. If the person is out of earth attractive, the gravitational field, so it's not attracted by the earth, that means it doesn't fall towards the earth. But do you fly away? Do you see this thing fly away like that? No, right? It is still at the same place near the earth, am I right? Yeah. So very interestingly, this fella is actually following the earth. This entire thing is moving like that together around the sun. You see that? Yeah. So I cannot say that there's no gravitational attraction on object like that. There will still be attraction. Just like you don't really feel it kind of thing. Just like when you're out of Earth, you don't feel the Earth gravitational field because Earth is a small mass. So when they're a distance away, for example, you're so far away like that, then you cannot feel it anymore. But somehow the sun is so huge, the mass of the sun is so much greater than Earth, the gravitational field strength can exert a pull on the Jupiter. Oops, sorry. Can pull on the Jupiter so far. What am I doing? Yeah. And this object here is going around. You see that? It's going around in the orbit. You can see that? Yeah. So if this Jupiter can be attracted and moved by the sun, any place nearer than Jupiter, we are all attracted to the sun actually. You know what I mean? So we are at a certain position. Okay, anyway, this one is very hard to imagine. Seriously, very hard to imagine. Because our sun is not stationary. Our sun is moving. Do you know our sun is moving? Our sun is moving. And all these planets are moving around the sun. So they actually spiral around the sun as the sun moving at a very high speed. Yeah,
Is it because of the
amazingly.
heat that attracts it?
Sorry?
Is it because the sun's heat attracts the planets?
Oh, no. It's not heat. The sun's heat is infrared radiation and it emits out. It doesn't go backward. It's just outward. It goes as far as, until it's very far dispersed. It is the mass. The mass of the sun attracts the earth. The mass. Okay, the particles inside the sun. Just like for example, I hold a mouse like that. The mouse is actually attracted to me, just like it's negligible. The mouse also attract my body, but it's negligible. We don't feel it, kind of thing. You know what I mean? But if my mass is great enough, I will attract. I'll attract towards it. If my mass is great enough, just like the sun attracts the earth, go round and round. And the sun attract the meteorite. Meteorite will fly in, go around the sun and fly out, right? A very large loop. I'm sure you have read this kind of thing or saw any video on the meteorite going around the sun and then fly off again. Yeah, it's possible. Are you there? Yeah. So anyway, in this chapter, all you need to know is this. Just need to remember a few where they won't test you too much. Basically, they may ask you MCQ lah. The only calculation is how you calculate weight. The weight, which is called gravitational force, is the gravitational field strength. All right. Multiplied by the mass. Yeah. Okay. So let's look at this. This is so the larger the mass, the greater the gravitational field strength. In short, we say greater gravity. Gravitational field strength is like gravity. All right. And then, of course, nearer to the mass, okay, the point near the mass experience stronger gravitational field. For example, you're talking about sun. Nearer the sun, you experience greater gravitational field. Any question?
No.
No. So all these are a bit abstract. Just try to understand them. And only thing you need to remember is how to use this one. Weight equal to mass time the gravitational field strength. Okay. All right. So let's look at this. A mountain climber carries a load of 20.0 kg. At 20 meters above the sea level, the weight is calculated, measured to be this. So what is the field strength? W equal to mg, right?
Yeah.
Field strength is a G. Wow. So what is G? You take the weight divided by mass, right? The weight divided by the mass. So you can take 196.2 over 20.0. And that is my gravitational field strength, okay? 196.2 divided by 20. Answer is 9.81 Newton per kg. Remember the unit, huh? Gravitational field strength is Newton per kg. Okay, next one. When it's high up in the mountain, 2,000 meters above the sea, very, very high up. This is at the sea level, very close. Very high up, you realize my weight has decreased. So 195.6 over 20.0. Let's try. 195.6 divided 20. And that is 9.78 Newton per every kg. Do you realize that my gravitational field strength has become lower now? From 9.81 to 9.78. Is it okay?
Yeah.
So on the mountain, what is my weight? My weight is equal to the mass times gravitational field strength G, right?
Mhm.
So it's 26.0 multiplied by G. This is a mountain, 9.78. All right, times 26. And my answer is 254.28 Newton. Okay? Exact value is this. Exact value.
Oh, okay.
Okay? Yeah. But we calculate, we base on the significant figure, the smallest significant figure of any given value. Let's count. There are 3 SF here. Okay, anyway, this is also 3 SF, nothing much. So 3 SF times 3 SF, my answer must left is 3 SF equal to 254 Newton 3 SF. Because this is 3 SF and this is 3 SF. Are you with me? So when you do calculation, you ask yourself who is the shortest or smallest SF. Then your answer is expressed as that one. Similar number. Is okay?
Yeah.
Okay. Okay, so okay, let's compare between mass and weight. Okay, just go through quickly because very easy. The mass is the amount of metal, how much substance inside the object. The weight is the strength of the gravitational force. The weight is gravitational force. Mass is a scalar, basically a quantity without direction, but the weight has a direction because you must ask yourself where does it go act towards. In this case, it's towards what? Towards Earth. Okay, direction towards Earth. The mass is kg for SI unit. Okay, the weight is Newton. This is independent of location. You don't care where you go, even on the moon, on the Mars, they are still same kg. But this one depends on the location. It depends on what? It depends on the gravitational field strength. It depends on the gravitational field strength. The greater the gravitational field strength, the greater is the weight. Now measurement, down here, very funny. Mass measured by beam balance. There are two balance, not beam balance. Electronic and beam balance. Let me write for you here. Electronic. I don't know why they do such thing. Okay, electronic balance is the more common exam standard answer. Beam balance is another one. All right, both can be used. And spring balance, the word spring balance here is for measuring the weight. Question? No.
How do you use a spring balance?
Okay, spring balance is very interesting. The scale on both sides. One side is Newton. For example, here is kilogram. So it's 1 kg, 2 kg, 3 kg. On the other side, the scale will tell you 10 Newton, 20 Newton, 30 Newton. Do you realize that it's directly proportional to the mass? The scale is drawn for you here. So instead of like one side is like that one. Okay. One side is kg, one side is Newton. So if 1 kg, you show you 10 Newton. 2 kg, you show you 20 Newton. 3 kg will be 30 Newton. and 4 kg with 40 Newton and so on. Okay, that's how you read from here. Instead of reading kg, you read the Newton, and that's how they measure the weight already. Is okay?
Yeah.
Okay, good. So let's look at this. There is no weight acting on the astronaut who is floating in outer space, the state of weightlessness. Okay, it's not true. It's just that it's not strong enough to pull the person into the atmosphere, right? So the weight acts on all objects that pulls them towards Earth, including astronaut, even though he's in outer space. Like we are all experiencing gravitational force from the sun, just that we do not realize that. So although the astronaut is floating and does not seem to fall, it's actually in circular motion around the Earth. So you're going round and round. How does it maintain round and round? It must be due to interaction of forces such that you don't go away, you don't fall inside. You just happen to go round and round in the same orbit. Means the outward force equal to the inward force. They're equal. Is okay? So when you come a bit nearer to the Earth, for example, the Earth is here, and then this is the orbit. The person experiences two forces actually. The force that acts outward and the force that acts inward. That's why you go in circle. And then the net force actually go in this direction. Net force. So that's why it follows a circular motion. Is okay? Yeah. So gravitational field strength has another name. Gravitational field strength is also equal to the acceleration of free fall. Acceleration due to gravity. Okay. The difference is this. The difference is gravitational field strength 10 Newton per kg. Okay, roughly 10. Okay, let me get just like the calculator here. This is a more exact one. Here, 9.81 is a more exact figure. So let's use 9.81. So per kg, the acceleration is actually 9.81 meter per second square. The value are the same actually. So gravitational field strength, unit written as how many Newton per 1 kg, is the same as acceleration due to free fall. It's actually 9.81 meter per second square. Okay, later you try to appreciate this thing. All right, let's look here. Okay, let's try this. I want you to try this. Can you see the whole question? Okay, this is the lunar rover. That means it's the robot. Okay, robotic thing that can move around, like a rover. The mass is measured to be 140 kg on Earth, and gravitational strength on Moon is 1/6 the G on Earth. Can you tell me what is the mass of the lunar on the Moon? Mass is 140 on Earth. What is the mass of the lunar on Moon?
On the moon.
Yeah. Do you think it's different? Will the mass change or not?
No.
No. So answer very simple. Same as this on top. On Earth, 140 kg. On Moon must be the same. How about the weight on the Moon? The Earth is 10. The Moon is 1/6 of the Earth. So what is the G on the Moon? G on Moon, right? Equal to 10/6. All right, 10/6. And that's equal to 1.666. And this one is the Newton per kg. Okay. Now, what's the weight? Weight is W equal to mass times G. And W is 140. And the G is 1.666.
Oh, okay.
Got it? Because this G is the gravitational field strength, the property of the planet. So time 140. And the answer is 233.33. And then give me 233 Newton. Okay? Let's talk about 233 Newton first. Then later you start answering why. Okay, now I want you to look at all the values given. the values given down here is 140 kg. How many SF is this?
SF significant figures.
Yes. The 0 at the back, do you need to count?
No?
No, right? So this is 2 SF, right?
Yeah.
2 SF. And of course, 1/6, these are just a whole number. Don't need to worry about this. So you realize the G actually is 1.666, whatever. So when you take the G multiplied by the M, okay, I know this number has to be 2 SF. So if this is 2 SF, the M must be 2 SF also. So in other words, in simple, 230 Newton, all right, bracket 2 SF. Any question? Is okay?
Yeah.
Can I say? Okay for you? If you're okay, then we move on.
Yeah. You're lagging for a bit just now. Sorry.
Hmm?
It was lagging for a bit just now.
Ah, okay, fine. I just wait for a response. Okay, come. Let's do this one. What is true about mass and weight? What is true? Yeah, I guess. If you can recall.
C?
Hmm?
C.
C. Okay, very good. All right.
I need help with understanding pressure.
Okay, can. So I'll just run through very quickly here. Density equal mass over volume, I'm sure you know, right? So higher density means you sink. So if the density is more than density of liquid, you will sink in the liquid. This is key concept. Density equal mass over volume. Remember SI unit kg per cubic meter. Can? Okay, let's move on now. Displacement method, you need to know how to find volume of irregular shaped object to find the density. So can use the displacement method. Okay, let's move on. Okay, is this the pressure? No, it's still density. Okay, good. So basically density will be length times breadth times height. Find the volume first. But down here you realize that all in cm. I want to calculate in this one. Look at this unit, cubic meter. So I divide by 100, divide by 100, divide by 100, then I multiply. This is cubic meter. Then I convert my 25 gram into kg. All right, 2.5 times 10 to the power minus 2 kg. So if you take the mass over volume, I will get my density in kilogram per meter cube. Okay. All right, come to pressure already. Pressure. Okay, pressure. What's the pressure? Measure of the force can change the shape. Huh? Wait. This is not a definition. Yeah, sorry. How a force can change the shape? Okay, no, it's not. This is not definition. A pressure can change the shape or even the size of an object, but pressure is defined as force per unit area. This is the definition. Force per unit area. All right. So basically, the greater the pressure, the more you can sink into another object. So here definition. Pressure is defined as a force per unit area. And you must remember that the force is Newton. All right. And the area is square meter. So Newton per square meter, or you can say Pascal. In simple, 1 Pascal equal to 1 Newton per meter square. That's what they mean. These are equivalent. Okay. 1 Pascal is as good as 1 Newton acting on 1 square meter. It's the same thing. And there's no direction, a little quantity, a number only. There's no direction. Okay. So pressure is a vector, of course not. Force is a vector, yes, but pressure is not. Okay.
Okay.
All right. Okay, let's look at how to calculate pressure. Let's look at this. A chair is designed so that can withstand the pressure acting on it. A lady sitting on a chair should exert a force. Let's highlight the force. 600 Newton. The total area of contact is 150. Calculate the pressure exerted. So in simple, pressure equal to force over area. The force is 600, is fine. But this is not SI unit. Must be careful. So let me calculate what is a cm cube to meter cube. A meter cm square to meter square. Look at this. 1 cm equal to 0.01 meter. Is it correct? Okay, I can start here, like 100 cm equal to 1 meter. So if you start 100 cm, 1 meter, 1 cm, 0.01 meter, I square both sides, 1 cm square, 0.01 meter square. So therefore 1 cm square equal to 0.1234 meter square. Am I right? So I divide by my area. Area is here. I divide here 0.1231. And answer is 600,000, I think, or 60,000. Eh? Sorry, 1.5. Why 1. Oh, I see wrongly. 1.150. So 150 cm square equal to 0.0150 meter square. See that? Because every cm square is 0.001. So if you multiply by 150 is 150, answer is here, this meter square. So I'm going to put it inside here. I'm going to put this value inside 0.0150. And let me press calculator. 600 divided by 0.015. Answer is 40,000 Pascal. Okay? There you are. Either I can put Newton per meter square SI unit or put Pascal. Are you with me?
Yeah.
Okay, I stop for a short while. Is there any question?
Like in my notes, right? Since I didn't have time to fill in, for this thing, is it correct?
Wait, let me see if I can see it. Give me a second. I adjust the view. Oh, yeah. Okay, I can see what? What's that?
Unit conversion.
Okay, yeah.
Is it like that? Do I have to edit it anymore?
Something is not right. Can you show me again? I want to see this first, second one. Down a bit. I look at B. Wait. Don't move. I cannot see clearly. Hey, what are they trying to do?
I'm not sure. It says unit conversion. I wasn't here that time, so I'm not sure what I'm supposed to do in this.
Okay. Yeah, here, look at this. It depends on what they want you to do. Okay, so let me show the unit conversion, right? For example, 1 Newton per cm square. If I want to convert to something, how many Newton per meter square? That's what they mean, unit conversion. From per unit cm square, convert to per meter square. And I want to convert like that also. I want to convert 1 Newton per meter square, convert to something Newton per cm square. Are you with me? So, sorry, this is square. So this is called unit conversion. Because Newton per cm square and Newton per meter square, they are both valid units of pressure. Okay? Okay, so let me run through with you. Let's do the first one. From here, convert to here. How do you do it? How to do here? Okay, let me move this away first. Oh, no, I leave it here first. So I start from doing this. My first step, 1 Newton per cm square is equal to 1 Newton per 1 cm square. Am I right to say that? So let me convert the below to meter. But I know that every cm equal to 0.01 meter. And then for 1 cm square, 0.01 meter whole thing square. So 1 cm square equals 0.1231 meter square. Do you agree with this conversion here?
How come we change it to a decimal instead of like 1,000 or something?
We change decimal. I square this, become this.
Oh, okay. Yeah, okay. I
Or I
understand.
can put 1 over 100 also can. So let's convert. 1 Newton I keep, but below I change from this to this now. Substitute inside. 0.1231 meter square, am I right? And that goes 1, 2, 3, 4. So equal to 10,000 Newton per 1 meter square. And that give me 10,000 Newton per meter square. That's what they mean. Unit conversion.
Okay. Okay, I see.
Can I say? So why not you try to convert this for me? One Newton per meter square equal to 1 Newton over 1 meter square. Then convert to cm square. Convert here. Can you do it? Can you convert meter to cm?
So, change into, wait, I'm very bad at conversion.
Don't worry, you start like that first. You always start from what you know, like that first. Am I right?
So
How
it
do you
was,
get? Yeah,
uh,
you square both sides.
yeah, okay.
Don't worry, we'll practice a bit more later. Huh? And you're going to get how many? You're going to get 40. Am I right? So I'm going to have 10,000 here. Okay? And this is as good as 1 times 10 to the power minus 4 Newton per cm square. Because, or I can write 0.000 3 zeros. You know what I mean? Yeah. Okay? Okay, now since you know this already, I want you to practice this one. Can you convert for me? Let's say you pressure, let's say 150 Newton per meter square. Can you convert to Newton per cm square? Can you do conversion for me?
So 150 will have to square.
No. You just have to convert 1 Newton per meter square to how many Newton per cm square. Then after that, times 150. Take it as 1 first. Okay? I can do this. I can do, okay, never mind. I think we'll do it separate, like you can do like that. Newton over 1 meter square can,
Oh, okay.
and then you convert the bottom. Convert the bottom to cm square. Can you do it for me?
So it becomes 100.
Square. It's not 100. More than that.
One,
Look at this.
100,000. Oh, okay.
10,000. 10,000.
Oh,
Okay? In this kind of situation, I suggest you press calculator. Because sometimes you shift here, shift there, decimal, then mess up already. So I take my calculator, I press 150, divide by 10,000. And answer is, you get this? Check your calculator.
yeah.
Simple, right?
That's right. In my physics paper, conversion is the one that I got all wrong. Even though the
Oh,
rest were actually okay. It's just my conversion I got problem.
okay. Then we need to practice a bit more. No worry, let's try. Next one, let's try next one. Now I want you to convert. Convert from Pascal to Newton per cm square. Just say, yes, 100,000 Pascal. Convert to Newton per cm square. But do you know what's Pascal not? Do you remember what's Pascal?
Not really.
Pascal is Newton per meter square. It's Pascal. SI unit. It's the same. So I just write like that first. Am I right? Then you convert.
Wait, Pascal has the same thing as Newton per
Per
meter.
meter square. Yes, same.
So is P on top, then A is at the bottom.
No. PA together one. I just need to know 1 PA is equivalent to 1 Newton per meter square. Because I want to convert this to Newton per cm square, I cannot, right? I must recognize it's Newton per meter square, then can convert. Pascal is same as this. So Pascal is same as this. So what? It's going to be like that. Look at this. Is it correct? Look carefully.
Yeah.
Then can you convert after this?
Oh, okay. I get now. Okay.
Yeah.
Is it 10?
Is it 10? Let me see. Yes, correct. So this one is as good as 100,000 Newton over 10,000 cm square. And that will cancel out for equal to 10 Newton per cm square. See that? Okay, let's do conversion. Something more interesting in terms of conversion is this. Since you want to practice a bit conversion, can we try speed conversion? I show you once, then you do. For example, I have okay, you know that the car limit is 90 km per hour. So let's put it into the fraction. It's 90 km per 1 hour, right? And then I want to convert the top and bottom to the other unit, meter a second. So km wise is 90 multiplied by 1,000. I change to a meter now because every km is 1,000 meter. Okay, I put a note here. 1 km is equal to 1,000 meter. And then below, I'll change to second. 1 hour equal to 60 times 60 equal to 3600 second. So it's turned to 3600 second. And then I press calculator. Answer is 25 meter per 1 second. And of course, 25 meter per second. That's how you do conversion. Convert the top and bottom independently. Then you write the new unit. Okay?
Yeah.
You copy it out first, then I let you practice. You convert for me this one. How you convert? 200.
So 200 over 1 hour.
Mm-hmm.
And then convert times 1,000 also.
Answer is how much?
Yeah. $55.5.
Okay, very good. 55.555, so it's 55.6, right?
Mhm.
Yeah. So I'm sure you have seen before on the on YouTube where car accident, the car flies across very fast, right? Traveling at this kind of speed. That means the car only take 1 second to travel 55 meters. It crossed the entire football field in 2 seconds. That's how fast it is. You see that? So a car coming at this speed, the person can never outrun the car. Because you are 50 meters away, the car reach you in 1 second. That's what I mean.
Oh.
Okay? Ah. Can I say right? Yeah. It may not look like a big number, but this speed is very, very fast, super fast. Okay? All right, now I want you to try to do the other way around. For example, I cycle a bicycle at 10 meters per second. I'm not sure whether how fast is that. So can you convert to kilometer per hour? 10 meters per second.
So now it's times, not
Now it's divide, not time, divide. Remember just now we time? Now it's divide. 10 meter over 1 second, right? Then you divide 10 over 1000. Convert to km. 1 over
just 260.
3600. So you press calculator and see what's the value. You need?
Kilometer per hour.
Very good. Okay, come, let's try another one. Okay, let's say this. 100 meters per second. Let's say a bullet fly 100 meters per second. What do you think is km per hour? Sorry, too easy. 120. Because you times 10 you can already. This one cannot.
Convert to kilometer per hour, right?
Yes, correct.
Okay. 432.
Okay, wait. Yes, correct. Very good. Okay, this is about the speed of airplane.
Oh.
Yeah. It's very fast, eh? The thing fly across the football field in 1 second. So in other words, you're standing at the goalpost. If the ball comes to you at this speed, you cannot even duck away. You hit you straight away in 1 second. Okay, good. Let's do a slightly different. Let's do density. Density, conversion. For example, water is 1 gram per cm cube. It can be written as 1 gram over 1 cm cube, right? Can you convert for me into kilogram per meter cube? Convert slowly. Okay. First of all, 1 gram is how many kilogram? Or 1 cm cube is how many meter cube? You must know how to calculate.
1 gram is 0.01 kilogram.
It's not 0.01. It's 1 over 1000. It's 0.00120. The best I write like that. Okay. It's 0.00001. How about cm cube to meter cube? That's quite difficult.
100,000.
More than that. Look at this.
1 million.
Look at this. Look at this, huh? I got cube both sides. Cube both sides. Okay. So this will be 1 over 1 million, right? And press calculator. Do you get it? Got it? Huh?
I've got 0.00, like a lot of zeros.
Why so small?
Let me check if I did it right. Hold on.
You press calculator correctly. You try to put a bracket around this one. Like that.
I got 1,000. I think I typed wrongly just now.
Okay, don't worry. Okay, now this is water. Huh? What does it imply? It implies that water, which is 1 meter by 1 meter tank, if you have a water tank, fish tank, 1 meter by 1 meter by 1 meter height, this entire thing is 1,000 kg heavy. Can you imagine? 1 meter by 1 meter, a bathtub and a small bathtub, 1 meter by 1 meter. It's not very big, you know. You know what's 1 meter, right? 1 meter times 1 meter times 1 meter, the entire mass is 1,000 kg. That's a lot. Okay? Okay, let me try now. Let's try another one. Go. 19.3 gram per cm cube. Can you tell me how many kilogram per meter cube?
Uh, 19.3 over 1,000.
And then after that,
1 cm over 1 million.
yeah, it's 1 over 1 million of a meter cube, right? Answer?
19,300.
Okay. Yes. You got it? And this number is humongous number actually. Yeah. It's a few like as heavy as a bus, a few buses. Yeah. The density is so huge. So 1 meter cube, 1 meter by 1 meter by 1 meter of gold, there's no way a person can push this. Even if I use my car to pull it, I can't even move. 19,000 kg, can you imagine? You know what I mean?
So, will it crush the wheels if like it's placed on a vehicle?
Yes, it be flattened. You need the kind of vehicle that carry the rocks, okay? Many wheel kind of vehicle to carry this 1 meter by 1 meter by 1 meter of gold. It's super heavy. Got it? Yeah. Okay, anyway, these are all the different conversions. I hope you're familiar now. Can? Okay, let's move on. You can practice more of that next time. So let's look at pressure. So pressure is Newton per cm square or Newton per meter square. If it's Newton per meter square, I can say that it's also equal to Pascal, right? So pressure can be measured, depending on what kind of pressure you're talking about. For example, you can measure the blood pressure of a person. You can measure the pressure of gas. You can measure atmospheric pressure to predict the weather and so on.
Does pressure of blood? Is,
Yeah, our blood has pressure, our body. That's the reason why when you poke, the blood spill out.
oh,
And you know the artery, the blood coming from the heart is higher pressure. That's why you see sometimes you watch movie, right? People shooting each other, then the blood spill out. And that's happened when the person got hit on the artery. The blood spill out. But if you hit on the vein, cut on the vein, the blood drip out. It doesn't spill like that. You know what I mean? Yeah, because the pressure for the heart is very high. So that's why it's very dangerous. If someone puncture the artery, like during wartime, you see the war show, like someone gets shot in the neck, the blood spilling non-stop. It's real. It's real. The blood cannot stop one. You know what I mean? Yeah. So blood has a pressure. And the moment the pressure drop means the person is dying. That's why you watch movie, right? The pressure drop and the heartbeat also go lower and lower, so the person actually die. Yeah. And usually a person injury, the pressure can drop if there's a leakage of blood inside the body. In other words, there's puncture in the artery, internal bleeding, then the pressure can drop. You know what I mean? So if you measure the pressure, suddenly the pressure drop, then you know the person has internal injury. So they must check which part of the body has a puncture inside. Yeah. Okay, let's move on. So down here, we learned a few things. To sum up, okay, this chapter sums up the force can change the stationary object to move, as well as changing moving objects to change its motion, direction, speed up, slow down, and so on. And a very important thing is the SI unit is Newton. You must know that. That's forces. And contact forces are friction, air resistance, tension, normal force. Non-contact force are gravitational, electrostatic, and magnetic forces. And the mass is a measure of the amount of metal, therefore it's kilogram. And the weight actually is a gravitational pull by the earth, is Newton. Okay, and the formula is actually here. The weight equal to mass times gravitational field strength. Okay, so the gravitational field strength is defined as Newton per kg. Density is mass over volume. Pressure is force over area. And then for density, SI unit is kilogram per cubic meter, while pressure is Pascal or Newton per meter square. These are SI unit. But be careful because down here, a common unit is Newton per cm squared. This is a very common unit in the exam. So you read carefully the question. Do they want you to calculate Newton per cm square or they want Pascal? If they want Pascal, then you give them Pascal or Newton per meter square. But if it's Newton per cm square, you just straight away divide by the cm square. You got the answer already. Are you with me?
So like, if they give the prefix, you have to follow that prefix. You cannot use others.
You can. It depends what answer you want.
Okay.
For example, they give you in terms of cm square, cm, all the measurement in cm. They give you in kg. They ask you to find pressure in Pascal, then you must change. Okay, give me an example. Oops, my pen will drop off. Okay, let's talk about an object here like that. Okay, this object is lying on the ground, flat on the ground, and this object has a let me think. Okay, let's say this object has density. Okay, let me include the pressure and density together. So this object has a density of, let's say the gold, 19.3 gram per cm cube. This is gold. And this dimension of the gold is, let me see, this is, let's say 10 cm, 10 cm, and this 5 cm. Find the pressure exerted on the floor by this piece of gold. First of all, find the weight first. Do you think you can find the weight for me? Given the
Weight changes on Earth and Moon, but it's the mass that doesn't change, right?
Yes, correct. Mass don't change. So down here, I need to find the mass first, right? Okay, so this cm by cm, all these are cm. So my volume, first of all, I must find my volume. Volume equal to 10 cm times 10 cm times 5 cm. And that gives me a volume how much?
500
cm cube, right?
Mhm.
Can I find the mass?
mass.
Formula density times volume. So my density is here. My volume is here. 19.3, right? Gram per cm cube. Multiplied by 500 cm cube, right?
Then you get 9,650.
Okay, this is gram, right? So now, before I can find Newton, I cannot use gram. No, I must find kilogram first. So how many kilogram is this?
Times
9
1,000.
divide 1000.
Oh, okay.
Yeah, 9.65 kg, am I right? So let's find my weight. W equal to mg equal to 9.65 multiplied by 10, assuming 10, the gravitational field strength is 10. So it's 96.5 Newton, am I right? Okay, let's find pressure now. Let's find pressure. Pressure equal to what?
Pressure. Pressure is force over area.
Very good. So what's my force? Force is weight, right? Area is what?
Area. Area is 500.
No, area is here. Area is here. Not volume, area.
Oh, so 5 times 10 meters.
No, area, the
Oh,
bottom
wait,
is
10 times 10 meters.
cm. Did I write wrongly? Okay, I think I better write probably for you. It is cm.
Okay.
Yeah, that's how we calculate is cm. See that we use cm, right? So I have 100 cm square, right? Yeah. So what's my pressure? My pressure is equal to 0.965
965. Is it wrong?
96.5 divided by 100.
Oh, yeah, okay.
0.965 Newton per cm square, right? Got it?
Mm-hmm.
But if I want to find Pascal, then how?
You just change the prefix.
Okay. Can you tell me how you change?
Instead of Newton per cm, wait, you have to convert to meter.
Yes,
Square.
correct. Convert to meter. So easier to convert here, no? Rather than here, I can convert here, right? Area is 0.1 times 0.1, right?
Mm.
Can you do it? So my pressure can be found as 96.5. No change. But I can divide by what? 0.1 times 0.1 meter square, right? This is 0.1 meter. 0.1 meter, am I right to say that?
Yeah.
So what's my answer?
Um,
9.
9,650.
Yes. 9650 Newton per meter square. Or I can write 9650 Pascal. See that? Yeah. You want Pascal, you make sure you convert to this first.
Okay.
Yeah. So that's the full working lah. So we are used to formula already. Can I? Okay, very good. I think we are done with this topic. Yeah, you try this question yourself, see whether you can do it. Down here never say anything, so you can use whatever they give you. Newton per meter square or Newton per cm square. Since they give meter, you use meter lah.
Yes.
Very simple. Can you try? Find the weight first. Now you get mg, right? Can you find me the weight?
80 kg times 0.020.
Why? Why so small? No, G is gravitational. It's 10 Newton per kg, remember?
Oh,
Gravitational field strength. Okay, let me type this out. You can write it down if you want. Gravitational field strength. Okay. Gravitational field strength. All right. So this gravitational field strength. Okay. So it's times 10. What did my answer be?
800.
Yes, 800 what?
800 Newton per, wait.
Not yet, not yet. 800 Newton only.
Okay.
No per. Okay, now you find me pressure. Pressure equal to what?
Force. The force is the Newton, right?
Yes, correct.
So it's
Force over area.
area, oh yeah, area is 0.020.
Yes, correct.
Okay. So it's 40,000.
Very good. 40,000. And you can write as Pascal. or you can write as Newton per meter square because they are same. Okay? All right. Is it difficult? No, right?
No, I think I'm getting hang of it. Yeah.
Hmm?
I think I'm understanding conversion better.
That's very good. Okay, let me see. Any more unit you can convert? Let me see. All right, we try this question here, this pressure also.
This is weight over kg.
Weight over G, you mean?
Yeah.
W equal to mg first, then W over G equal to M, right?
Mm.
Therefore, my mass equal to 600 over how many?
10.
10, yes. 10
So
Newton per kg. Answer is?
60 Newton.
Are you sure?
60. Wait. Wait.
Newton divided by Newton per kg. What do you think become?
Kg.
Yes, correct, kg. Be careful, because it's a mass, so it must be kg.
Okay.
Okay, next one. And the blade, this blade pushes the air down, so it can uplift, right? A force, upward force. So what's the pressure acting on the motor by the air? You got the weight, 600 Newton. You got the area. So can you find the pressure?
60 over
Wait,
1.
why 60? Why 60? Isn't pressure equal to force over area?
Force. Wait. Force is the weight, right?
Yes, correct.
Okay. So it's 600 over 1.2.
Yes, very good.
500.
Units?
Uh, PA Pascal.
Yes, correct. Or another unit is what? Another unit could be,
Newton over meter square.
yes, correct. Yes. Okay. Can. So usually, if they give Newton and meter squared for calculation, I can just leave Newton per meter square lah. But I also can put it as Pascal if I want to. It's okay?
Mm.
Oh, good. We have finished this chapter already. Okay, let me, yeah. Any question to ask on this?
No.
No. Okay, this one is just mass and weight calculation, so I won't go through. You can just do yourself.
Okay.
This one you may want to go through this review. Yeah, you may want to go through this. This is quite interesting question. What are the forces that acts on the ladder?
Ladder.
Mm,
Ladder or
against the wall.
um, forces. So gravitational is always going downwards.
Mm-hmm. W is all correct actually.
Oh. N is Newton, right?
Yes. No. This is not unit. This is just a label. It's called normal force. You know normal perpendicular to the surface.
Yeah.
Yeah. So this I just put for you. This is called normal force.
Wait, but what's the difference? They all look the same.
No, look carefully. There's slight difference. Very slight difference. There's only one force that's different for all of them. The normal looks the same. The weight looks the same.
Oh, it's
Friction is different.
friction. Okay.
Tell me which one is the friction so that the ladder do not slip and fall down.
D.
Hmm?
D.
D?
Because the friction is going downwards.
No, imagine the ladder try to go downward. The friction must push against it.
Also, it should be C.
See?
Because it's against the wall. Wait. Force should be on the floor, right?
Yes, more on the floor. Yes, you're right. Friction is more on the floor. The wall actually very little friction.
So it's A.
Yes, answer is A, correct.
I see.
You see, this friction prevent you from slipping. Do you remember if this thing slip, what will happen? It just go down, right? Because the friction here is minimal actually, compared to this. This is a lot. Okay?
Yeah.
Yeah. So at least recognize that they ask you to draw all the forces. Look at these forces. The forces normal because it push against the wall. So this is perpendicular to the wall, out from the wall. Likewise, this one is perpendicular out from the floor. Normal, they call normal force. This one is perpendicularly down because gravitational force is acting vertically down. Okay? And imagine this ladder going to slip, and what prevents from slipping is the friction on the ground. So this one must know. Exam, they may ask you to draw all the four forces in a diagram like that. Possible. Is it okay?
Yeah.
Good. Right. We are done with this topic. I stop here first. Give me a second.